Very good. Our next speaker, Dr. Amy Rovelstad, is a manager in the Modeling and Simulation Department in the Science and Technology Division at Corning Incorporated. Prior to joining Corning in 1997, she worked for two small startup companies located here in Washington, D.C., as well as at the Army Research Lab in Adelphi, Maryland. She received her PhD from the University of Maryland, College Park, and was an NRC postdoctoral fellow at the Naval Research Laboratories, again here in D.C. Amy has been a champion in developing Corning's capabilities in materials modeling. She has been the manager of the Materials Modeling Group in the Modeling and Simulation Department since 2007. Thank you.
Thank you. So I wanted to start off, since I am the representative of Corning here, and we Gorilla Glass, which is used on a lot of the smartphones. The people that did not raise your hand when you were asked whether or not you had smartphones, I want to encourage you. I think there should be some gift-giving occasion coming up soon, so please, go out and make that investment. So I'm going to take a little bit lower view than the previous speakers. I'm going to really talk about what this looks like kind of on the floor of a materials modeling department in a corporation, and you'll hear a lot of the same sorts of themes, but they might sound a little bit different. So first of all, I want to start off with a couple of somewhat high-level observations about what innovation looks like today. So first of all, the increased use of modeling to maintain our competitive edge is not an option. We really don't have any choice. We have to do this. Other companies are doing this. Other countries are doing this. We really have to do this. The cost and pace of innovation has increased significantly over the last 10 years. Product cycles that used to be measured in years are now measured in months. And furthermore, the specifications are getting tighter and tighter. And so, I'm calling it Edisonian because I'm being polite as opposed to trial and error. They just aren't going to work. I mean, they can't get you. They cannot get us where we need to go. We don't have a choice. We really need to do this one way or another. So there's this strong and increasing need for engineers and scientists with a background in modeling. And I want to point out here, I'm not saying materials modeling in general, and actually from our perspective, some of the modeling that was talked about earlier, we would call that process modeling. But that's the direction it's going pretty much across the board. Materials modeling is actually lagging a little bit in some of the other modeling techniques, but that has to happen as well. So with that, I want to start with my summary, which is going to build on that a little bit. So first of all, again, use of materials modeling has to continue to increase for U.S. corporations to stay competitive, both with other U.S. Corporations as well as with corporations in the rest of the world. So we need to have a strategy to train both our current and our future workforce in order to be able to use these techniques. And that's going to require collaboration and work from pretty much everybody. Industry, universities, and government are all going to have to work together in order to be able to get workforce in place. And I would be remiss, I guess I'm going to be repeating some of the things that have been said before, but from a different perspective. A lot more work remains to fill in the modeling gaps. The models are not complete and they're not mature. And we need to be able to make them relevant to industrial applications. In a lot of areas, that's not the case yet. So let me talk a little bit about what this looks like from Corning. So Corning Incorporated, we're one of the oldest U.S. manufacturing companies, founded in 1851. We're headquartered in the southern tier of New York State. We have about 26,000 employees worldwide. We are a global company, and an increasingly global company, and we're the world leader in specialty glass and ceramics. And the rest of this slide is really just kind of taken up showing the various businesses we operate in and the various kinds of products that we offer. And a lot of business analysts look at this and they find it kind of confusing because it looks like awfully broad. And how do they analyze us? But for us, it really boils down to two things: state-of-the-art revolutionary processes and state-of-the-art revolutionary materials. And if we can lead in those two areas, then we can come up with products that are going to be successful in the marketplace. And that's how we think about the work that we do. So, how do we use modeling in order to be able to do this? So basically we use it everywhere. It's applied in fundamental research, and we are, I think, one of the few companies left that actually do fundamental research in our labs. Applied research, development, manufacturing, and all of the businesses that you saw there, they all use some amount of modeling. And I have a little graphic there showing the sorts of activities that you might use modeling for in the various parts of the innovation cycle, research, development, and manufacturing. Materials modeling to date has pretty much been concentrated in R&D because that's really where the state of the models are. But I don't think that this is, it's going to have to follow the same path as process models and other sorts of models. It's going to have to be extended to engineering and production in the future. And that means not just PhD scientists and engineers are going to be able to use these tools. They have to be developed to the point where engineers on the floor and technologists are able to use some of these tools. And that's a challenge for us to be able to get to. So materials modeling at Corning, historically it's been limited by computational capabilities, the range of techniques and expertise available. And basically the computational capabilities and range of techniques meant that you couldn't really access systems of industrial relevance very easily. They were kind of limited to very academic exercises. But in the last 10 years or so, that's changed. With the advent of bigger computers and more models that have been kind of being developed in the universities and in other research areas, we are now in a position where we can actually start to use these sorts of models for things that we care about. So in Corning, we've spent about the last 10 years really trying to build up our capability in this area. We have done this historically at kind of limited ways, but we've really focused on it in the last 10 years to get the tools in it. And a lot of times, as I said, these tools don't exist, and we have to go and invent them to get the things that we need for our applications. And I'm going to give an example of that. So the example that I wanted to talk about today is glass compaction. And so what does that mean? Well, basically, glass is a non-equilibrium material, and I'm showing here a plot of volume versus temperature. And what that means is that as I cool the glass from its liquid state, depending on how quickly I cool it, it can end up with a volume at some relatively high level, or if I cool it more slowly, it will end up at a somewhat smaller volume. And that's because it's a non-equilibrium material. We capture that through a thing called non-equilibrium viscosity. And why do we care about that? Well, the problem is that when we sell the sheet to our customers, they're going to do processing on it after that, which is probably going to require heating and cooling the sheet. And if we heat it and cool it in ways that we don't know, we can't understand and predict and help them with, what will happen is that the sheet changes dimensions, and that does things like change the pixel size and distort your image, and our customers get testy about that. So we need to be able to predict what's going to happen when they do these kinds of processes, and we didn't have very good models in order to be able to do that. There were some phenomenological models that had been developed 50 years ago that people tried to apply, and they did something, but they were kind of limited utility. We really needed to drive it down so that we could have a system that we could actually predict and understand. And one of the people in my group actually did that. John Morrow went and he used all of the methods that he had available to him and a few others that he invented. Electronic structural calculations, molecular dynamics calculations, energy landscape calculations, and he really fully characterized a simple glass, so selenium glass. And he could use that to kind of as a sandbox, to try to test some of his methods, some of the other methods he was going to come up with. So he validated it. Here's a plot of this non-equilibrium viscosity that we use in order to be able to capture this behavior. Essentially, it's a function of temperature. And since it's a model, of course, we can do all kinds of things that we can't possibly do in real life. So this is covering cooling rates from 10 to the 12th kelvins per second to 10 to the minus 12 kelvins per second. It's 25 orders of magnitude. And we compare it to experiment, which is this little line shown here. And so you can see that, it looked like he was going in the right direction. Whoops. He could then validate it against and compare some of these other phenomenological techniques and against using his data. And this is showing essentially this log viscosity is a function of temperature, fictive temperature, and inverse temperature essentially. And his is the model shown here, and here is one of these phenomenological models that have been developed 50 years ago without being able to kind of access this kind of data. So obviously it's doing a better job there. You could then use that and parameterize it, come up with these new models that he can now extend to more complex silicate glasses. And then we can validate it against these more complex silicate glasses. So this, for example, is a deflection experiment that we did using our Corning Eagle XG product, which is probably what you have in your TVs. And these are just simple deflection experiments. Basically, you take a piece of glass, you hang away from it, you put it in a furnace, and you let it deflect for a while, and then you compute and measure the amount of deflection. And he compared it to a number of these other again, these other earlier models, and this is the kind of agreement he was able to get with those, and this is the kind of agreement he's able to get with the data with this new. You can see he's doing a much better job going deep and really understanding what's going on here to be able to predict behavior, and that is a big advantage for us because now we can either help select a glass that is going to be appropriate for our customers' processes, or we can help them develop processes which are not going to result in bad outcomes for them. So this is a reference, here for this particular some of this work if you're interested. So that's an example of what the sorts of things that we're trying to do. So we need to continue to build on this. So what is our current strategy? So we know we're going to have to hire some more people, so we need to build it into our hiring plan. And that means, periodically we're going to continue to have to hire people that have the right expertise in these areas. What we're really doing, though, is doing a lot of internal training. So we've sent people back to school to get their PhDs. We do a lot of on-the-job training, and we're doing what we can in order to fill this need. We're also having to develop the models and techniques that we require. They're not really out there yet. We have to do it ourselves. But we certainly want to make use of anything that we can get that somebody else has developed. So we do participate in external connections such as consortia and collaborations and directly sponsoring university research. There are some issues. The first one is one that you've heard before, which is we just don't have that many candidates to select upon. Right? As a hiring manager, when I go out and I'm looking for somebody to take a job, I have a lot of trouble finding somebody who's qualified. Again, there's these gaps in the models and tools. I think particularly in glass and ceramics, they may be a little bit behind some of the alloy models. And there's huge gaps in physical properties. We really need to get much better data for physical properties because, as you heard before, kind of garbage in, garbage out. So I'll leave you again with my summary. This is an important area for us. It has to continue to increase if we're going to remain competitive. Our competitors are doing it, and need to be able to run faster than them. We need to develop strategies to fill the needs that we have coming. We see them coming; they're already here. We need to figure out how to do this, and that's going to require everybody figuring out how to work together. And then again, my last complaint is there are still work that needs to be done to fill in some of the modeling gaps and to make them relevant, particularly to industrial processes.